surveys that will be able to test general relativity and also the CDM model on large case and illustrate deviation from GR, given, for instance, by dark energy and modified gravity. At the same time, we recently had a series of new important probe of gravity, the observations of gravitational waves. And in particular, these observations will be richer in the future. The number of events will practically blow up exponentially. And they will allow us to probe again gravity, either in using the emission of gravitational waves or the propagation. And in this talk, I will focus on the propagation. And in particular, to give you a message to take home, I would like to show that the gravitational wave observations severely constrain cosmological modifications of gravity. I will focus here on theories of modification of gravity based on a scalar field, and in particular on theories that display self-acceleration and screening. And in this case, they also dramatically reduce the parameter space of these theories, and therefore the discovery potential of eventually on new physics from larger structures. Okay, so typically when discussing about dark energy, I mean in the simplest setting, one considers a Lagrangian which depends on a scalar field phi and its first derivative. However, recently there has been a lot of studies in considering theories where higher derivatives become important, as important as the lowest derivatives within the validity of the effective theory. And this is because these higher derivatives can be used to provide self-acceleration, basically acceleration without a cosmological constant, and screening, which allows to screen modifications of gravity effects on short scales in order to pass solar system and other gravity tests. So there has been a sort of there have been a lot of studies around a particular set of theories that are called Ordansky theories. These are the most general covariant theories with second-order equations of motion. The reduction of second-order comes from the fact that we want to avoid Ostrogowski instabilities. And actually, one can add to that other functions, or let's say other operators that display equations of motion that are higher order, but once you write them in terms of the true degrees of freedom, propagating degrees of freedom, you see that because they are degenerate, they display also the same number of degrees of freedom as Ordansky theories, and therefore are free from Ostrogowski instabilities. So I will focus in this talk on this particular set of theories, and in particular I will consider let's say a subset of these theories that display nice quantum mechanical features. So you can write, let's forget for a second about gravity. You can write Ordansky theories in terms of a series, a Taylor series of these coefficients of x, which is basically defined like that, divided by lambda 2 to the fourth, and d squared phi divided by lambda 3 to the cube. So lambda 2 is a scale defined like that. So H0 is the Hubble rate today. So this scale becomes of the order of 10 to the minus 3 electron volt, and is related to the symmetry breaking scale in a cosmological setting. Okay. Lambda 3 is defined in this way. and is much smaller, so it's about 10 orders of magnitude smaller than lambda 2, and it is related to the UV cutoff of this theorem. So you see that in the limit where lambda 2 goes to infinity and you keep lambda 3 constant, and these coefficients here depends very mildly on the scalar field, so are basically constant, you recover the Galilean Lagrangians that Lavinia showed earlier, and the Galilean symmetry. And it's because of the symmetry that so let's say you can see this theories here as a sort of weakly broken, a version where Galilean symmetry is weakly broken and is realized in the limit where the ratio between the two scales become very large, and you forget, of course, about gravity. So because of the non-renormalization theorem that you have in the presence of Galilean symmetry, also in this more general case, you will have a sort of weakly broken non-renormalization theorem in which higher order operators are generated by quantum fluctuation, but they are suppressed either by higher order derivatives or by the ratio between these two scales to the power 4, which is an extremely small number. Okay. So we can reintroduce gravity, and if we do that, in general, Galilean invariance will be broken. However, if you do it by maintaining exactly the or density coupling, the approximate Galilean symmetry, the Galilean invariance will be maintained, and therefore also quantum correction will be under control, exactly like in this case. And it has been recently shown that this extends also to beyond order density theory. Okay, so this is why it's interesting to consider this particular set of theories. Okay, another reason why these theories are interesting, I think, is that they have been studied also from the observational point of view, in particular by using the so-called effective field theory of dark energy. This is something related to Shinji's talk, in the sense that in the EF theory of dark energy, you know that there is a scalar field that breaks time diffeomorphism, and you can write down an action in terms of all possible operators invariant under the remaining diffs, which are special diffs, ordered by number of perturbations and derivatives. And when you do that, you obtain a series of operators that you can parameterize in terms of dimensionless functions for convenience, and they allow to connect these general covariant theories. Once you focus on perturbations, you can connect these covariant theories to observations in a systematic way and using the minimal number of free parameters. So this has been done, for instance, to build Einstein-Boltzmann codes that can generate various observables like the CMB or the matter power spectrum in terms of these dimensionless parameters. And you can use these Boltzmann codes and other codes to make forecasts. And most of the forecasts that have been made point out to the fact that future Lasser structure observations will tend to put constraints on these alpha parameters that basically parameterize extension of lambda CDM up to at the order of the percent, of few percent. Okay, so let us see what we can do compared to this few percent with the gravitational waves. And in particular, so I will describe gravitational waves by using the symbol gamma ij. So this is the traceless and transverse part of the spatial metric. And I will focus on the propagation of gravitational waves. And we know that in standard GR, gravitational waves display a wave equation with some friction term that is due to the Hubble friction, but here we can completely neglect in what I will saying, and they propagate at the speed of light, as you know. So the first thing that you can have in these modified gravity models, so since you are breaking by the presence of the scalar field Lorentz invariance, you can have different phenomena that you typically have when you break Lorentz invariance, and one of these is refraction. So the fact that the gravitational waves can propagate at a different speed than the one of light, and this is for instance, the same as what happens when you send the light through a medium like water, for instance. So this has been constrained, as you already know, by the observation of gravitational waves and gamma ray burst emitted by the merging of the neutron stars in the 1708-17 event, and the constraints are very tight because these effects accumulate over a very long time of propagation of the gravitational waves. And let us quickly check what are the constraints on these theories. You all know in this case, if so many of these operators contribute to change the time kinetic term of the gravitational wave, and therefore, if you want to tune the speed of propagation to be the same as the one of light, you have to basically tune some of these coefficients or some of these functions, and in particular, you will have to get rid of two of these functions, so G5 and F5, and the other two of these functions, in particular F4 and G4, X, where the comma is the derivative, will have to be the same. Okay, and notice that this tuning is stable quantum mechanically because of the symmetry, the Whitley-Bock and Gallino symmetry that we discussed earlier. Okay, so at the end of the day, we are left with this much simplified theory. But before discussing what we can do about these theories, whether we can constrain it even more, let us just mention a caveat that has been raised by Claudia and Scott after these studies, and is the fact that, of course, here we are assuming that the same effective theory that we use on cosmological scales is also applicable on LIGO-Virgo scales, which may not be the case, especially given that LIGO-Virgo scales is very close to the cutoff of the theorem. So the theorem may break down and new states appear, and at a scale which is lower, parametrically lower than the cutoff lambda 3. And the speed of gravity can be different from one on large scales, on cosmological scales, and become one on LIGO-Virgo scale. Of course, in this case, one would have to find a way to reconcile local tests of gravity, which are currently explained in terms of Weinstein screening, and in this case, the situation would be totally different. But a more, maybe an interesting question would be to try to explore this setting by using, for instance, this analyticity and causality constraints, analogously to what you can do, for instance, for light in a material when you study Kramers-Kronig relations, for instance. Okay, so let's go back to the Lagrangian after having set in the speed of propagation of gravitational waves to 1. In this case, let's define two-dimensional parameters that will help us to the following analysis. And one of these parameters is alpha h, which is defined as, well, x squared f4, so this function divided by g4. This g4 is basically the effective Planck mass squared for this theory. And this constraint, alpha h is of course related also to this function because in this setting these two functions are related. And we can call this a sort of beyond Ordansky parameters because it parameterizes how much beyond Ordansky you have in this theory. And then you can have another operator which is the cubic, well, generalized cubic Galilean, or Briding operator, which I parameterize in terms of these dimensionless parameters alpha b, defined this way. And I remind you that these parameters will be constrained from future Lasky structure surveys at the order of a few percent. Okay, let's start to look at this beyond Ordansky operator. And in particular, let's take the theory in the presence of this operator. And sorry, no, before doing that, we are going to look at the two other effects that you may have in the presence of spontaneous Lorentz breaking, which are absorption. So the fact that the gravitational wave can be absorbed by a medium, in this case they will decay, and dispersion, so the possibility of having an anomalous dispersion relation, different from k squared, for instance. These two effects are actually can be related by the optical theorem, and I will essentially focus on this, but I can discuss this one if you want later in the questions. Just to mention that the constraints on this effect are inversely proportional to the distance from the source to the observation. Again, because they accumulate over the propagation of the wave, and they are also inversely proportional to the frequency of the gravitational waves. And you can observe them by just comparing, since they are frequency dependent, you can just compare to different frequency, and the constraints that you can put on them are very tight. Okay, so let's focus, as we said, on alpha h, on this beyond Ordansky theory, that we can expand in terms of the gravitational wave and the scalar field, the fluctuation that I denote by pi. So apart from the quadratic Lagrangian that it's here written in terms of canonically normalized fields, I can have nonlinear couplings that are proportional to this alpha h parameter. I have a self-couplings of the scalar field surprised by the scalar lambda 3. And then I have a coupling between the gravitational wave and the scalar. One is surprised by lambda 3 and the other one is surprised by lambda 2. Let me forget about this one, which basically doesn't give any observable effect, and focus, let's focus on this one. So this this operator can display, can give you a decay of the gravitational wave into fluctuations of pi, if the kinematics allows it, and this is the case if the speed of propagation of pi, of the dark energy fluctuation, is smaller than the speed of the tensor modes, which is the speed of light. So the probability amplitude to have this decay is proportional to alpha h, and to the to 2 powers of the momentum of the gravitational waves, which come from the fact that here in this operator you have 2 derivatives on 2 time derivatives on the gravitational wave, and then well, depends on the polarization, and is proportional to the momenta of the pi field. And once you can go on and compute the decay rate, and at the end you find that the decay rate is proportional as expected to alpha h over lambda 3 cube squared times the frequency of the gravitational wave to the power 7. And since the LIGO Virgo band is very close to lambda 3, this decay rate becomes of the order of lambda 3. And since this is much larger than h, well, than the traveling time of the gravitons, by just requiring that you don't see any effect due to the decay of the gravitational waves, you can set a tight bound on alpha h, which is of the order of 10 to the minus 10, so much tighter than what you can get with large structure observations. This, of course, unless the speed of the pi fluctuations is very close to the speed of light. So actually, similar constraints can be also derived for CS larger than 1 by considering the anomalous dispersion relation that you can find from this coupling. So in these constraints, we are assuming that you have a single graviton, basically, that decays in 2 pi fluctuations. But of course, a gravitational wave is made by many more gravitons. Is a collection of a lot of gravitons with a large occupation number. And we may wonder whether the decay is enhanced by this fact, by the fact that we have a large occupation numbers. Similarly to what you have when you compare reheating, which is a perturbative decay after inflation, and preheating. So we have extended this perturbative study to this non-perturbative, this coherent decay. In this case, we are going to consider the gravitational wave as a classical wave. For instance, let's assume it as just a plus polarization. And we introduce an important parameter for the rest of the talk, which is called beta, and it parameterizes the size of the effect in general of the gravitational wave on the propagation equation of the pi field. Beta is proportional to alpha h, and is proportional to the square of the frequency of the gravitational wave. And the fact that it's a square comes from the fact that in this operator you have again 2 time derivatives. And then, of course, it's proportional to the size of the gravitational wave. So in this setting, we are assuming that the speed of propagation of the pi field is smaller than the speed of light, so that the past light cone, the past pi cone is smaller than the light cone, than the light cone of the gravitational wave, and basically pi sees the gravitational wave as something homogeneous. For instance, it doesn't see the source, but once you fix the point Q at this point, it sees the gravitational wave as something homogeneous, and this is why, although in general gamma is inversely proportional to the distance from the source, here we are assuming that the gravitational wave is uniform. Okay, now when you go to Fourier space, you can write this wave equation as wave equation with time dependence frequency as a Mathieu equation, as people who studied preheating, for instance, know well. And Mathieu equation display on the plane A and Q, which are defined this way, instability bands where you have an exponential growth of pi fluctuations. In the case where we are in narrow resonance regime, so where beta, this parameter here, is much smaller than 1, it's possible to compute analytically the rate of decay, the rate of growth of this pi field, and this is what we did, and we managed to compute the energy density of the produced pi, and then to compute the back reaction on the gravitational waves, which is finally what really sets constraints on the parameter alpha h. Okay. Okay, so now I will show the constraint that we were able to derive. These constraints are a bit strange because there were many approximations that we used to derive them. And so they only hold when these approximations are valid. And here I'm assuming two typical frequencies. One is a LIGO Virgo frequency, and the other one is a frequency. And so we are in the our approximations are realized when we are in narrow resonance, so not here, but below this line, when the effect is large. Sorry, I forgot to mention that these constraints here are on alpha h as a function of the distance of the effect that takes place from the source. Okay. So if this effect takes place too far from the source, the amplitude of the gravitational waves is too small, so the effect is also too small. And then we have to neglect self-couplings. So if you remember earlier, I showed you that the scalar field pi has some self-couplings, and in general, these self-couplings can destroy the narrow resonance regime by taking modes in the resonance band out from the resonance band, basically. So in order to avoid that, we have to assume that that the self-coupling are negligible, and in this plot, this happens when you are above one of these two lines, and depending on how much you want to consider these nonlinear couplings. So at the end, you can draw some constraints on alpha h in the LIGO Virgo band, going by 10 to the minus 20 to 10 to the minus 16, and in the LISA band, going from 10 to the minus 16 to the 10 to the minus 10. And you see that they complement in a way the constraints that we were able to derive from the perturbative decay, so that at the end, the alpha h parameter seems to be strongly constrained. Okay, so at the end we have this theory, and we can get rid also of this operator, at least for what concerns cosmology. Okay, this operator, we know it's extremely small for cosmological purposes. Let's focus on this one, and let's see whether we can use the same logic that we used earlier for the gravitational wave decay, knowing that in this case, we have a coupling between the gravitational wave and the pi, which is surprised by lambda2, so a much larger scale than lambda3. So as we expect that, for instance, if you compute the decay, the perturbative decay, you see that this is negligible. Okay, so we can try to compute the coherent decay. However, you see that the nonlinearities in the pi field are surprised by lambda3 instead of lambda2. So these are immediately very important with respect to the coupling with the gravitational waves. And in principle, they are going to immediately quench the exponential growth. Of course, in order to make a proper analysis, one should be able to implement some numerical simulation, which is beyond our scope, as it has been done, for instance, in the case of preheating. But at least we don't see any clear constraint on alpha b to be derived from the decay. So we decided to explore another regime, which is instead of the narrow resonance regime, is a broad resonance regime, in the sense that we take a beta to be much larger than one. So at first sight, if you look at this equation, it seems that this regime is problematic, because you see that here you can have a gradient instability, because the square of the speed of propagation can become smaller than 0. It can become negative. Okay, so of course this conclusion, although it is correct, it's a bit premature. What we should do more properly, and what we have done, is to is to, well, first split the pi field into a background part, which varies slowly and which is sourced by either matter or by the background of a gravitational wave, and then consider fluctuations on top of this background, and look at the propagation equation of these fluctuations in the presence of this background. So in particular, you will have this effect here, but you will also have the effect of the background scalar field, which is sourced by the gravitational wave, to take into account. Anyway, at the end of the story, so you have gradient instabilities once you have imaginary solutions to this equation for some k for momentum k mu. And you can have ghost instabilities when the 0,0 component of this matrix is negative. And at the end of the day, well, I spare you the details. One finds that you have both gradient instability when beta is larger than 1, and also ghost instabilities when this condition is realized. Okay, so give me a couple of minutes to discuss when this instability is triggered, and then I will discuss what this instability means in this context. So in order to see whether the instability is triggered, we have to, for instance, we want to see when this beta is larger than 1, we said. So the beta parameter now depends on alpha b, and is proportional to 1 power of the frequency of the gravitational wave, because the coupling between gamma and pi contains a single power or a single time derivative, and is of course proportional to the amplitude of the gravitational wave, which is proportional to the chirp mass of the objects and to the frequency, to the power of 2/3. And is inversely proportional to the distance from the source. Moreover, this relation that we will use assumes that we are below, the frequency is below what is called the innermost stable circular orbit frequency, where this approximation is roughly valid. So we can consider stellar mass objects like those that can be seen by LIGO and Virgo, but in this case, in order to have a sizable effect, but not to end up to have a frequency much larger than the ISCO frequency, we can consider only distances from the production of gravitational waves of the order of 1 megaparsec, which is done here. And we see that, so we can derive some constraints on alpha b as a function of the speed of propagation of the pi field. And once we put together the condition to avoid the ghost and to avoid the gradient instabilities, we find that alpha b must be smaller than about 10 to the minus 2. These constraints are rather rough. Of course, what we can conclude from this is that you can trigger instabilities around the dense regions, and this was more or less expected. It would be nicer to show that you can trigger instabilities everywhere, and this can be done if you consider a larger portion of the universe, for instance, 10 to the about 10 megaparsec, that where you can consider that the universe is roughly homogeneous. And if there is at least one black hole that triggers the instability there in an Hubble time, you can be ensured that the instability is triggered everywhere. And in fact, so here in this plot we are showing so we are showing the value of the value of beta equal to 1 for different value of alpha b, and different value of distances from the source. And for instance, let us focus on this alpha b equal to 10 to the minus 2, which is the one that we were interested in. You see that this happens at roughly at a distance of 1 megaparsec, or almost 10 megaparsec. Okay, but if you go to slightly larger values of alpha b, you end up in 10 megaparsec. And you can see that so if you consider population studies of black holes, of massive black holes, they show that you can have between 5 and 50 supermassive black holes with masses between 10 to the 7 and 10 to the 8 in a portion of 10 megaparsec, which will induce an instability in this frequency band, which is which corresponds to very long wavelength, down to 10 to the 10 kilometers. So that our conclusion are very safe, very far away from the UV cutoff of the field. Okay, now there is the question of what this instability means. Is this instability real? So are there observational consequences? Well, in principle, so you may have a gradient and ghost instabilities appearing in a low energy effective field theory of a stable, completely stable UV complete theory. So in principle, this could mean that the instability could mean that we are just in a region of the parameter space where the effective field theory is not valid, okay? Because the regime of validity of the effective field theory depends, of course, on the energy at which you are, but also on a particular background, for instance, in this case, on the background of the gravitational wave. Moreover, if you compare the typical energy density of the instability, which is saturated at the cutoff, so it will be of the order of lambda UV or lambda cube, for instance, to the 4. This is much smaller than the typical energy density of the gravitational wave that is unfortunately lambda 2 to the power 4. Okay. So we don't see any possibility for physical effects on the gravitational waves. What we can say is that once the instability is triggered, you cannot trust the effective field theory any longer. So if you want to make some prediction on the behavior of pi, you cannot use this effective field theory. Notice that the constraint that the alpha b values above which you have an instability are very close to the constraint that you can reach with large structures. Okay, I think I can conclude here. So I discussed that the fact that gravitational waves can probe already modify gravity similarly to how you use light to probe materials, and in many cases they are very effective, much more than large structures. We have seen the constraints coming from the speed of gravitational waves that remove a part of this Lagrangian. We have seen the use of the perturbative and resonant graviton decay in constraining the beyond Ondesky operators, and we have studied the stability of a gravitational wave that make you lose trust in this particular theory for values of alpha b that are large. Thank you.
Thank you very much, Filippo, for the nice and clear talk. Yeah, I think we can, I can see one raised hand is Maria. Please go ahead, ask your question.
Hello. So one question, I might have a couple, I don't know, is about the resonant decay. So during inflation, for example, I understand the inflaton oscillation can be treated as a condensate because it's a coherent oscillating field. How does it work in dark energy? How do you get, do you also have a field oscillating? I'm not very familiar, that's why I'm asking. How do you get that phenomenon?
So in this case, the analogous of the inflaton, of the coherent inflaton oscillating is the gravitational wave. So the gravitational wave is a coherent wave oscillating, and this is the background. So you see, yeah. So what you in general in preheating you have an oscillating inflaton field which is coupled to a lighter field chi, and in this case the pi field is the analogous of the chi field in the preheating.
Now understand. Yes, and very quickly about the speed of sound in this resonant decay. Does it play a role how small the speed of sound of the scalar field is?
So we assumed in our analysis that the speed of sound is not is neither too small nor too close to 1, because so it has to be smaller than 1 to have this narrow regime, and also for our approximation to make sense. But we didn't consider the case where the CS is very close to 0, for instance.
Is that gonna, can you constrain that, or is it a possibility? And will that affect your resonant results, your
so I think that you have to if I remember, so if some of my collaborators remember, so let me think about that, and I can reply on Slack. I think there is probably the cutoff of the theory, but I have to.
Perfect. Thank you.
Great, thanks. The next one is Guy.
Hi. Two quick, I guess they're related. One is, if you could measure polarization of the gravitational waves, would it buy you something like having a bound on the size of, say, the monopole to the transverse traceless parts of the gravitational wave? And related, like, would the shape of the gravitational wave be degenerate with the usual inference of like the parameters of the binary merger?
So when you say polarization, meaning if we were able to measure both both to observe also scalar fluctuations emitted, right? Or
yeah, that's right. I mean, you can't do it with interferometers, but maybe with a bar detector, for example, you could measure a monopole or something like that.
Yeah. So we didn't go so far as to study that, also because the scalar fluctuations are generated by the travel with a speed which is much smaller than the one of light. So in principle, they will not be received. So they will be received after a long time. And so our constraints were derived by the assumption that you don't see effect in the gravitational wave itself.
Okay, and then just a quick follow-up. Can you say something about the shape? Would the shape of the gravitational wave tell you something about what the theory is?
So you mean the waveform, or?
Yes.
Okay, so well, again, I don't think we went into so much details, but one thing that we did is to study. So sorry. Yeah. So let's consider this case, for instance. So what we studied was the effect, the back reaction of the pi produced. So the gravitational wave produces pi, and then this back reacts on the amplitude of the gravitational waves, which is changed. And for instance, if you start, in general, a gravitational wave is elliptically polarized. So you have a combination of both polarizations. But if you start with one of these polarizations, you end up by changing only this particular polarization. And okay, you can study how the growth rate depends on the polarization, etc. One thing that you can see is that you have a sort of higher harmonics that are produced by this effect, and these higher harmonics will reach. So we call them precursors because they will reach the observations early, since they are at higher frequency. They reach the interferometer earlier than the main signal. So yeah, so this is one thing, but then yeah, I don't know if this answer to your question.
Yeah, that's great. Thank you.
I think maybe we have just half a minute for the very last question, Angaran.
Oh, sorry. Yeah. Thanks, Enrico. Yeah. Thanks for the great talk. I just want to ask quickly. So when you're talking about the high harmonics, are you referring specifically to the the inspiral asymmetric? Like you'd see those high harmonics in like asymmetric binaries. Things like that. Just as regards to Guy's question about the shape of the waveform.
Sorry, say it again.
So the higher harmonics, like when do you physically see those? Are you saying specifically for like something like an asymmetric binary?
Asymmetric meaning what?
Sorry, as in like you don't have like two even mass binaries. So.
Oh, sorry. No, this is independent on the mass ratio.
Okay.
You have it in general. Yeah.
Okay, sure.
Okay, well, thanks a lot, Filippo. And as Filippo also